In this lecture, we are going to check our understanding of the ACF and PACF in code. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As always, you can check the lectures, how to code by yourself, and how to practice for a more in-depth discussion. If there's anything in this lecture you didn't understand, or you think I missed a step, or didn't explain why we were doing something, please use the Q&A to inquire. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. So the first thing we're going to do is import plot PACF and plot ACF from stats models. These are more useful than just generic ACF functions that only give you back an array, since these will make a plot and draw the confidence bounds automatically. Next, we're going to import NumPy and Matplotlib. Next, we're going to generate IID noise from the standard normal. Just to build a point of comparison for what we will see later in this lecture, let's plot what this noise looks like. Okay, so I'm pretty sure this is not too surprising. Next, let's call the function plot PACF. We'll be looking at autoregressive models first, and as you know, the relevant plot for that is the PACF. Notice that I'm using the subplots function to manage the size of a plot. This returns an axis object, which I then pass into the plot PACF function. Alright, so what do we see? Well, as expected, most of the lagged PACF values are very near 0. The first value is 1, since that's just the autocorrelation of each point with itself. Notice how there are multiple values in which the PACF goes just outside the confidence bounds. However, you have to remember the definition of the confidence interval. Basically, this is allowed to happen randomly 5% of the time, even when there is no true correlation. Since these values are so close to the threshold, we can intuit that it's probably okay to ignore them. Next, let's create an AR1 process and test the PACF again. To generate this process, I'm going to create a list called x1 with an initial value of 0. Then I'm going to enter a loop that goes for 1000 iterations. Inside this loop, I'm going to create the next value by taking 0.5 times the previous value, plus some Gaussian noise with standard deviation 0.1. We'll call this variable x. Next, we append x to x1. When we're outside the loop, we cast x1 to a NumPy array. In the next block, we plot x1. As you can see, it looks pretty stationary, and there's no real observable difference between this and IID noise. It's not obvious that each value depends on the previous value. Next, we plot the PACF for x1. As you can see, we have a PACF value at lag 1, which is far outside the confidence threshold. Therefore, if we were to look just at this plot, we would conclude that our time series is an AR1 process. And of course, we know that this is true because that is what we just created. Next, we're going to do another experiment, again for an AR1 process. I'm not going to run through the details of this code again, since it's very similar to last time. The main difference with this code is that the coefficient for the previous x term is now negative 0.5 instead of positive 0.5. We'll see what effect this has on the PACF. If we look at the plot of the time series, again, it's not at all obvious that this is any different from just plain IID noise. Alright, so next we look at the PACF. This time, we see that there is again a non-zero value at lag 1, but this time it's negative, corresponding to the negative coefficient of our AR1 process. Next, we're going to generate an AR2 process. So this time, the time series will depend linearly on 2 past values instead of just 1. To initialize our list, we'll set the first 2 values in x2 to be 0. Inside the loop, we use the following equation. The coefficient for the lag1 value is 0.5. The second coefficient for the lag2 value is minus 0.3. And again, we have Gaussian noise with standard deviation 0.1. From our time series plot, it is again the case that we probably cannot distinguish this from IID noise, although the variance in the later parts of the time series seems to be quite high. If we look at the PACF, we can see that there are now 2 non-zero lags, corresponding to the 2 coefficients of our AR2 process. The first non-zero value is positive, and the second non-zero value is negative. If we were to use this plot to choose the value of p for fitting an autoregressive model, we would definitely choose 2, so this confirms that this method works. Next, we're going to generate an AR5 process. To initialize x5, we'll create an array of all zeros. Inside the loop, to generate the next value of x, we will make x depend on 3 different lagged values, rather than all 5. In particular, these will be the last value at t-1, the second last value at t-2, and the fifth last value at t-5. The weights for these will be 0.5, minus 0.3, and minus 0.6 respectively. Again, we'll add Gaussian noise with mean 0 and standard deviation 0.1. Notice that when we plot the process as a time series, it definitely looks a little different from IID noise and all of the previous plots. There seems to be more of a pattern and a more wave-like structure to the time series. Next, we plot the PACF. Notice something interesting with this. Even though our time series does not depend on the lag3 and lag4 values, the corresponding values in the PACF are still non-zero. So although we generated the process ourselves, and we know that it doesn't depend on the lag3 and lag4 values, when we fit an ARP model, we will always include those terms. So this is a sign that, just because you have some in-between values that don't affect the next value in a time series, this does not mean that their PACF values will be 0. Alright, so since this lecture has been pretty long already, I will see you in the next lecture to look at the ACF and moving average models.